Hello, in this video I would like to try to shine some light on a Fourier transform, what a convolution is and how we can use it, what is a transfer function and what is an impulse response of a linear and passive system, and how they are all connected to each other and can be used to simulate or to analyze system. And in this process we will also use a Heaviside step function. It will be probably a longer video, so you better grab some tea or coffee. And the example that we will use for this is some simple RLC circuit, because this is something that every electrical engineer should know. And for to get some better idea about this, I will use an LTspice simulation. So as a component, as the source, as our input, I will use a voltage source, and then we will have the RLC circuit with R, L, and C, and the output at the end should be the voltage drop across the capacitor. And of course we also need to have our ground node, reference node somewhere. So I will use the wire tool to connect everything together and draw this loop, and also connect the ground node, and then I will label this node here on top as the voltage of the source, and I will label this node here as the voltage drop across the capacitor if we measure the voltage there, and this will be our output node, let's say. So then all the parameters need to have some values. So I will set the resistor to 0.5 ohm, and I will set the capacitor to maybe 1 millihenry, and the inductor and the capacitor to maybe 10 microfarad. And the source should be some pulse source. So the initial voltage I will set to 0, and the on voltage is 10 volt with 5 milliseconds of delay, a very short rise time. Ideally I would like to set this to 0, but I can think 1 nanosecond should be small enough, and the on time of the pulse should be 10 milliseconds. So this is our pulse description of the source. I will move this to this side a bit, so that it's better readable. We can start the simulation, and I will simulate maybe something like 50 milliseconds, and also skip the initial operating point solution, so that at the beginning there will be no current through the inductor, and there should be no voltage drop across the capacitor and so on. Okay, and so then we can check the input voltage, which is our nice pulse with 5 milliseconds of delay, switching on, switching off, or stepping up, stepping down with 10 volts of amplitude. And if we check the output voltage, we can see, okay, if there's no input, nothing happens at the output, obviously. And then we switch on, so we kind of start some oscillation here in this resonant circuit, and then it's nicely oscillating, damped by the resistance, and then we switch down, we start another oscillation, it's ringing down, and we end up with something like 0 volts for the output voltage. After a while, of course, it will get smaller and smaller and smaller, but here we can almost see no oscillation anymore. Okay, so this is what is really happening. This is a time domain simulation of our circuit. So the second thing that I will do is I will open up a new schematic, and I will try to copy all stuff from the first schematic to the second schematic and zoom back, and now change the source. So we don't want to have a transient source anymore. Now we would like to do AC analysis, look at the transfer function of this circuit. So I will set the AC amplitude to 1, all the other parameters will be the same, but we need to change, of course, the simulation command. And from instead of transient analysis, we will do AC analysis, and we will do a decadic sweep with maybe 1,000 points per frequency decade, which is already quite a lot, starting at 100 Hertz and maybe ending at 10 kilohertz. If you use the values of RL or of L and C and calculate the resonant frequency of the circuit and or the resonant angular frequency and then the frequency, you should end up with something like between 1 and 2 kilohertz. So in this range we should see the resonance. And okay, so then with this circuit we can also start to do the simulation here and get a second plot. And if I also take a look at the output voltage here, then we can nicely see, okay, it's starting with here, so it's dB scale, so it's starting with 1 because at low frequencies the capacitor is acting like an open circuit, and so there will be no current, and all the voltage of the source will be visible as a voltage drop across this capacitance. And then for higher frequencies there will be some current passing through the capacitor, and there will we hit this resonance point, and then for higher frequencies the impedance of the capacitor gets smaller and smaller and smaller, and that's why the voltage drop across this element gets smaller. So this is the transfer function. By amplitude, this is the solid curve, and by phase, this is the dotted curve, and we can see that the phase starts with 0 degree and then goes down to minus 180 degree, and exactly at the resonance we have a phase shift of minus 90 degree. Okay, so time domain and frequency domain behavior of the circuit very quickly simulated in LTspice. So the next step is I will use Octave. And in Octave, I would like to replicate the behavior of the circuit at first in time domain. So I will go to the editor and we'll start with a clear all and close all, so that we always start with a clear workspace, close all open diagrams. And of course, we need to have the values of the parameters. So we will start with 0.5 ohm, then the inductance is 1 millihenry, which is 10 to the power of minus 3, and the capacitance is 10 microfarad, which is 10 to the power of minus 8. Now we need to have the parameters of the source, so the voltage should be 10 volt, the delay time before we really switch on the pulse should be 5 milliseconds, so we also choose this milli or 10 to the power of minus 3 there, with 5, and our pulse width tau should be 10 milliseconds. Okay, so then the next step is we need to have a time range, so our ending time should be 50 milliseconds as in the LTspice simulation. Then we need to have a time step, and so as you could see here, this resonant frequency was between 1 and 2 kilohertz, so the corresponding periodic time there would be 1 millisecond or half a millisecond. And so if we want to have a reasonable resolution here for our transient simulation, then we need to have time steps that are much smaller than this. Let's say hundreds of this, something like this. So I will go for 1 microsecond, and this is definitely much smaller than 1 millisecond or half a millisecond. And it means that if we simulate 50 milliseconds, that we get 50,000 time steps at the end, which looks or sounds reasonable. Okay, so then we can set up a vector of our time steps. It will start at 0. We take this step and we take this ending time, and then we should get 50,001 values for the time. So then next step is we could define our pulse here, our source voltage, and for this we need to have the before mentioned Heaviside step function to to have to switch on, or step up and switch off, step down again. So I will define this Heaviside step function as a function that depends on time. And it should be the case that if the time is larger than 0, so as you can see here, then this will switch to logically 1 and we get 1. So using this Heaviside step function, we can write our source voltage as a function of time. And so it's a Heaviside step function depends on time. And after this delay time, we want to switch on. And after another pulse with tau, we want to switch off again. So this is switching on, switching off, and we need to multiply with the amplitude of the pulse, which is u. Okay, so this should be our source voltage. Maybe we can plot this and check how it looks like. So as a function of time, we plot the source voltage. We are real engineers, so we also label our axis, say this is the time in seconds, and on the y-axis we have the voltage in volt, and a grid would be nice. Okay, and so now I can run this. I will save it as transient versus FFT versus convolution. And there's a plot. The plot is always appearing on my second screen, and we can see, okay, we switch on, we have 10 volts, we switch off. That's our input voltage. Okay, so I will maybe comment out the close also that the plot stays at the same position. So the next thing that I would like to do is to replicate this transient simulation here by more or less solving Ohm's law, law of induction, and conservation of charge in the circuit to replicate this behavior. So to do this, we need to have a loop over all time steps. So NT should be the number of the time step. And so I will call the length of this vector here capital T, so the time steps count from 1 to capital T, 50,001. And okay, the loop will end somewhere. And inside this loop, I now need to do some stuff. So let's move my Octave window a bit over here. So we need, at first, maybe what we need is, what are the initial conditions in our circuit? And the initial condition is that the current as function of time is 0 at the beginning. So the inductor is uncharged. There is no magnetic field in this inductor. So I will use zeros, lots of zeros in the same dimension as this vector. And the same thing is what I will use for the voltage across the capacitor, which is our output, because the capacitor should also be uncharged at the beginning. And okay, we also have a voltage drop across the inductor, and we have a voltage drop across the resistor, and I will all set them to 0 at the beginning. Okay, so now inside this loop, we can see what we have. We have the current as an initial condition should be 0. So if I know the current, I can calculate also the voltage drop across the capacitor, across the resistor. This should be resistance times times current, and the current at this time step. So in the first time step, the current is 0, so also the voltage drop across the resistor will be 0. We also know that the voltage drop at the capacitor at the beginning should be 0, because this is some initial condition. So we can calculate the voltage drop across the inductor by using Kirchhoff's voltage law. This is some Ohm's law. Now we use Kirchhoff's voltage law and say it's the source voltage at this time step minus the voltage drop across the resistor minus the voltage drop across the capacitor. So this should give us the voltage across the inductor. And yeah, at the beginning, this will be 0, this will be 0, everything will be 0, but later on we have a source voltage and therefore we will get some voltage drop across the inductor. So now if we have a voltage drop across the inductor, the current through the inductor will change, and we only have this current, this one current inside our loop, so we can calculate the current change or the new current from the old current, and then plus the current change, and the current change depends on the voltage divided by the inductance multiplied with our time step. This is how, if you would rearrange the law of induction at the inductor for discrete time steps, you get this solution. Very simple, stepwise staircase approximation of the integral that happens there. Okay, so we get a new current, and if we now know the new current, we can also calculate the new voltage across the capacitor. So new voltage at the capacitor can be calculated from the old voltage at the capacitor using the current that we just calculated divided by C and then also multiplied with the time step. Okay, and these last two steps do not need to be done, which is kind of the update, let's say, do not need to be done if we are already at the last time step, because we won't use these values anymore. So I will say if NT is smaller than capital T, if we don't have the last time step, then we will do this, and so for the last time step we won't do this, let's say. Okay, and so this should calculate my output voltage. Now I think I can move this plot command to the end and say instead of only the source voltage, I will also plot this output voltage. And because we now have two curves, we also need to have a legend, and inside this legend we have input and output voltage. Okay, and if I run, hopefully something should happen. There is my diagram. So now we can see, okay, nice, we get the same result as in LTspice, looking pretty similar. Voltage, output voltage is 0, of course, at the beginning. Then we switch on. We see this oscillation, damped oscillation. We switch down. We start another oscillation, damping, and then we finally end up with something close to 0 again. Okay, so first result, we nicely replicated, or I nicely replicated the transient simulation here in LTspice. Of course, in LTspice, it will be a bit different because LTspice will automatically choose nice time steps. There will be some more sophisticated formulas for the integration. But at the end, we could say, okay, what is happening here and what is happening here is more or less the same, or at least it's pretty similar. Okay, so the next thing that I would like to do is I would like to use this frequency domain description of the circuit, this transfer function, let's say. And so for this, I need to have two more functions that are somewhere here in my folder already. It's a function for a Fourier transform, and there's also a function for some inverse Fourier transform that have been developed by my colleague, Dr. Kochetov, a couple of years ago, as you can see, and I've edited them a lot and modified and changed and improved them a bit. So the idea of this Fourier function here is that you give time steps and the corresponding values of the time function, and you get back frequency values and the corresponding spectrum. And in addition to the FFT or built-in FFT in Octave, you don't need to care about the scaling, so this function will do the scaling for you. And there's a mode here also modus, and you can set this to pulse or to sine, and we have kind of a pulse, so we will set it to pulse. And this Fourier function will help us to take our source voltage, use this pulse mode, and then from the source voltage and the time calculate the corresponding spectrum of the source voltage as a function of frequency, and also corresponding frequency steps. So from the frequency, we can calculate angular frequency, which is just 2 times p times f. And then, yeah, we need to somehow calculate this amplitude response here. And the amplitude response is just the voltage divider. Output voltage is proportional to partial impedance divided by the total impedance multiplied with the total voltage, which is the input voltage. So we need to have the impedances of the capacitor, which is 1 over J times omega times C. And we need to have ZL, which is just J times omega times L. And this is a vector. We want to do element-wise division, so we need to have this dot operator there. And so using this, we can calculate our transfer function. And as said, it's ZZ, the partial impedance, divided by R plus ZL plus ZZ, which is the total. The total impedance. I will escape the output here and there. And also here at this position, we need to have this dot operator to have element-wise division. And if we run the script until there and check the result, we see, or we should see, that the first frequency here as an output from the Fourier transform is 0. So the first angular frequency is also 0. So here we divide 1 by 0, which should be infinity. And if we then divide infinity by infinity, we should get not a number. And this is of course not good. So if we, from this transfer function, if we check the first 10 values, okay, we can see we really get this not a number. And then we get something close to 1 with a very small imaginary part, something a bit larger. So the first value, in this case, infinity divided by infinity, should be 1. So we set the first value of this transfer function to 1. And then, no problem. Now it's, no, I mean, this is not really complicated, but now it's getting much easier because we can just take our transfer function, multiply the transfer function with the spectrum of the input voltage, and then we should get the spectrum of the output voltage. So the complex phasors of the voltage drop across the capacitor as a function of frequency. And once we have this, then we can use this inverse Fourier transform. And so take this spectrum, take the corresponding frequencies from here, of course use the same mode, and then go back into time. And this time here will be a bit different. It will not be exactly the same time as we started with. So that's why I will call this T2. And we get, we should also get our voltage drop across the capacitor as a time function now from the FFT. And I will escape the output and once again move this plot command to the end. So now we have a second time vector T2, and with respect to this T2 vector, we can plot the second result from the FFT. So we need to expand the legend, add something to the legend. This was the output voltage from the transient simulation. And the third curve in this diagram should be the output voltage from the FFT. And we have a grid also. Grid on. Okay, so I will run the script and check the window. And okay, it's calculating something here. There is still some, maybe I need to escape this output here. And there is some error in line 41, I think, which is this one here. Yeah, of course, this is a vector and this is a vector. So this should also be a dot multiplication, element-wise multiplication. So let's run again. And there it's finished. And there's the plot. And as you can see, now we have two curves. And the two curves are nicely on top of each other. If I zoom in and if I zoom in more, okay, then you can see there's a slight difference between the curves, but in the overall picture, there's a very nice agreement between these two results that are, and this is from my point of view always very fascinating. Yeah, so we have calculated the output voltage by two completely different ways. The first way is to do a pure time domain calculation by solving, doing a numerical solution of the corresponding differential equation. And the second solution is, okay, we have transformed the input voltage into frequency domain, calculated the spectrum, multiplied the spectrum with the transfer function of our circuit, and converted the result back into time domain. And because we did it right, we get the very same result at the end, as you can see here. Yeah, the zoom is a bit confusing me. What is kind of interesting, of course, is that if you zoom in, here, for example, at the beginning, and if I zoom in a bit more, oh, then you can see that the output voltage calculated by the FFT shows some kind of uncausal properties or some uncausal behavior, because there is some oscillation already before we switch on the circuit. Yeah, so this oscillation that we've just seen happened here. And the reason for this is it's kind of an artifact of this FFT, because we are switching on. So we are starting this oscillation, it's ringing, it's damped, and we switch off, it's ringing, it's damped, and still we have some very small oscillation here at the end. And now the FFT assumes that this time function would replicate. So because it's still ringing here at the end, we also see this ringing here at the beginning, because it's replicating, and we start once again, and then it's ringing down, and we start over again, and so on. So for the FFT solution, we would probably need to wait longer or damp it more, so that we don't start with an oscillation already at the beginning. This is some problem, some artifact, as said, of the FFT. Okay, so the last thing that I would like to do in the script here, after we have now checked what is the transfer function and how does this Fourier transform helps us, we would like to go to the impulse response and to the convolution. And the impulse response is the Fourier transform of, or the inverse Fourier transform of our transfer function. So if we don't do this inverse Fourier transform of the output spectrum, but if we take our transfer function, calculate the inverse Fourier transform of the transfer function, we get the so-called impulse response. And if we use this impulse response, and now, as mentioned here, calculate a convolution. I don't know where in this long article is explained, but this is the way how a convolution works. If we now, as before, don't multiply transfer function with input voltage spectrum, but if we calculate a convolution between the impulse response and our input voltage, then we should also get the output voltage. And convolution can be done with this command here, conv. We have the two vectors that should be convoluted with each other, and then we will just use the default setting of this full convolution. So I can try to do it like this and say the output voltage, the voltage drop across the capacitor from this convolution should be, we take the convolution and take our input voltage and calculate the convolution with, not with the transfer function, but with the impulse response. And before we do so, maybe let's check this impulse response. So I will run this line, and we can take a look at, or we can also try to plot this impulse response. And then we can see, oh, this is looking strange because, yeah, it's not a curve. It's more like some Nyquist plot or so. So if we check the first, or if we check some values of this impulse response, maybe the first 10 values, we see, okay, due to some numerical uncertainties and so on, they get a very small imaginary part. This impulse response should be a purely real function, but we get some imaginary parts. So if we check how large are these imaginary parts there that are just displayed as zeros, we can see, okay, they are very, very small. Some has 10 to the power of minus 12 or 13 or 14 even. So in comparison with this value, it's really, really small. So from this impulse response, I will just take the real values. And then do the convolution. And so if we check the length of this impulse response, we can see it's 50,002, because this time here, the T2 is also 50,002 values. At the end, I would only like to have 50,001, so I will cut the last point and say the impulse response is just all values until end minus 1. So here I should get 50,001. Once again, this is also 50,001 points. And so if we check now here what is written in the manual, the result of the convolution should be 50,001 plus 50,001, which is 100,002 minus 1, which is at the end 100,001. Okay, so this should be the length of this. And yeah, and we can calculate this convolution. And so this will be 100,001 values, and then I will just cut them to the first 50,002, which are fitting to our transient simulation that we did before. So I will take all values until t, the number that we calculated here before, the 50,001. Okay, and so then in my plot here, I have a last command. So with respect to t, I can also plot the output voltage as a result of this convolution. And I'm not sure, maybe I should better do it with T2 here and maybe cut it to the length of T2. Maybe this makes more sense because it's a little bit more related to this time steps that we had here. Okay, and so the last entry in the legend then should be from the convolution. And I can run the script. And there should be some plot then opening. And then, okay, we can already see the same curve, the same behavior as before, but now we get extremely large values here, something like 10 to the power of 6, 10 to the power of 7. And this is because our convolution that we calculated here is just a numerical convolution of these two vectors. And in the real convolution, we integrate over time. And so the time range or the time step is missing. And if we take this convolution and multiply it with our time step that was called, oh, not delta t, but t step, and run the script again and check the plot, then we should get now 3 curves for the output. One calculated directly in time domain using this transient simulation, one calculated purely in frequency domain, more or less, let's say, by the multiplication of the input spectrum with the transfer function and then converting back using some inverse Fourier transform into time domain. And the last thing is we calculated the transfer function in frequency domain, converted this back into time domain, got the impulse response, and then calculated the convolution between the time function of the input signal, which is the step, convoluted with the impulse response, and then also got this nice result. And so if I zoom in, and once again zoom in, and once again zoom in, then you can see, okay, these 2 curves for the FFT and for the convolution, they are very, very close together. And the line that is a bit off is the transient simulation. Yeah, and why? Because from my point of view, this approximation that we have done here of the integration is just very, very rough. As said, like a staircase approximation, it would probably be better to use some kind of trapezoidal rule for the integration there. But overall, this all works very well. So we can describe or simulate systems directly in time domain. We can use this transfer function and Fourier transform approach, or we can use this impulse response and convolution approach. And if we do it correct and right, we should get the same result each and everywhere. And of course, all these different methods have their advantages and disadvantages, but the idea is that usually it's much simpler to calculate this transfer function here in frequency domain. Yeah, here it was just a simple voltage divider instead of really thinking about Ohm's law and Kirchhoff's voltage law and law of induction and conservation of charge. So this, of course, is much simpler, typically much simpler than this. So this is one easy way to go also for more complicated systems or circuits or whatever you would like to simulate. And if we zoom in into this first range here, then we can see the method with the convolution also does not have this acausal or uncausal ringing problem. The convolution is also really 0 at the beginning and just starts to jump up at the place where we have some excitation here. Yeah, so the FFT solution is starting with the value of 0, but convolution and transient simulation, they really start with 0. Okay, so this is the comparison that I would like to show in this video. I hope you enjoyed it. See you later.